All right, for number 39, it says that the roller coaster is frictionless. You have a 100 kilogram mass here. Okay, and it starts from rest. Sometimes if it starts from with a certain speed, you have to take into account the kinetic energy. And it goes over a hill that is 10 meters, over a hill that is 10 meters and 8 meters high. Okay, how much work is needed to lift the car to point A? Well, to bring it up to here, you have to work against gravity. So basically, you just have to do the work is equal to the mg times the height. And you should get 100 times 10 times 10. Okay, and that should be your gravitational potential energy. And that should be about 10,000. Okay, what is the UG of the cart at point A? Well, the work that she did to bring it up here now became gravitational potential energy. That should also be 10,000. What's the kinetic energy at point A? Well, the kinetic energy at point A is 0 because you're starting from rest at point A. What is the UG at point B? Well, if we look at this level here as our reference for gravitational potential energy, then we can say that the gravitational potential energy at point B is 0. If we had chosen point A as the reference, we should say that the gravitational potential energy at point A is 0. But I always recommend that you choose the lowest point of your problem as 0 for gravitational potential energy. What's the kinetic energy at point B? If you do the conservation of energy, you do UA, UGA, I guess. Well, there is no elastic, so I'm just going to say UA plus KA. That should equal to UB plus KB. Kinetic energy here is 0. Gravitational potential energy here is 0. So whatever energy you had here in the form of gravitational potential energy becomes kinetic at the bottom. Okay. What is the UG of the car at point C? You do the same thing. Point C, you have UC plus kinetic energy at C. The only difference is that at point C, the gravitational potential energy is not 0. So basically, the kinetic energy at point, what is it asking? The UG. So I think to find the UG, just do MGH. To find the kinetic energy at point C, you just do the difference between UA and UC, because these two are equal. There's no work being done between any points of this problem. So the energy is the same everywhere. So it just changes shapes. So if you are here, you're losing gravitational potential energy and you're picking up kinetic. If you're down here, picking up more kinetic at the expense of gravitational potential energy. What's the velocity at point C? Well, once you find the kinetic energy, you use the formula K equals 1/2 mv squared, and you should get 6.32. Number 40 is really similar to the previous one, so I'm going to skip it. Okay. Okay. Let's look at this RT22. Okay. Shown are blocks that slide down frictionless inclines. All masses start from rest at the top of the incline. Rank the kinetic energy of the sliding masses the instant they reach the bottom of the incline. Now, this is frictionless. So there's no friction being done as they slide in down the ramp. So whatever energy you have at the top of the ramp has to be equal to the energy you have at the bottom of the ramp. Now, all your energy at the top of the ramp is in the form of gravitational potential energy. So how do we rank this? We rank them based on their gravitational potential energy, because that's going to be converted to kinetic energy at the bottom. And the ranking should be F, A, and C together are equal. In other words, you're going to do MGH. Okay? Yeah. If the masses were the same, we'll just do H. And here you don't even have to do MGH if you think about it. MGH, right? So the G is constant to all of them. So I think if you just do m times h for all of them, and that's your explanation. Okay, and then comes then E, B, and D. Okay, and that's just by doing m times h after you explain that G is constant for all of the MGHs. Okay. Now we're looking at RT23. In each case below, an arrow has been shot from the top of a building, either up. Can you plug in the power? I think it's dying. On the side, I think it's loose. See, it's loose. Just move. Can you move the laptop? Yeah, it's not making good contact. Right, that's it. There you go. That's it. It stays. Just check on it once in a while. It's good. All right. Thank you. That was Maria Chong, by the way. Okay. Has been shot from the top of a building, either up at 45-degree angle, straight out horizontally, or down at 45-degree angle. Now, what we have to get from here is that the kinetic energy is the same regardless of how we fire it, as long as we fire it with the same speed. And the reason for that, because kinetic energy is a scalar quantity, we no longer have to deal with this angles business. All the arrows are identical, meaning they have the same mass and it's shot at the same speed. So their kinetic energies are the same in all cases. Okay, but the heights are different. Rank the speed of the arrow just before they hit the ground. So I'm going to write an equation for a general case, and then we're going to apply it. So kinetic energy at the top plus potential energy at the top equals kinetic energy at the bottom. This is the conservation. There's no air resistance here, right? It says to ignore it. Okay. Now, the kinetic energy at the top is the same for all of them, and this is part of your explanation. Okay. So which one is going to have the highest kinetic energy at the bottom? Is the one that starts with the highest gravitational potential energy at the top. And since they all have the same mass, it's going to look like this. mgh is 1/2 mv squared. V at the bottom here, right? So the mass is irrelevant, okay? So basically the one with the highest V is the one that's going to have the highest GH, basically. And the ranking should be C and E tied, and they come first. Then A is sandwiched in the middle, and B and D are tied, and they come at the end. Okay. Number 24, RT24. Okay. It's a roller coaster that's designed to launch the riders over an alligator-infested lagoon. I don't know why you would do that, but the frictionless coaster starts at point A, starts at rest, so there is no kinetic energy here, so you only have gravitational potential energy at point A. The coaster lands on a ramp on the other side of the lagoon. After it is airborne, will the maximum height be greater, less than, or equal to the height at point A? Well, when it's doing this, it's kind of like fired as like a projectile. Okay, so when it lands there, I'm sorry, it lands here kind of, I guess, and it just continues. All right, so when it's at the maximum height, this height has to be less than this height here. And the reason for that, because you have all this gravitational potential energy that's going to be converted to some form of energy when you are here. But when you are up here, keep in mind, you're still moving horizontally. You stopped moving vertically, but you're moving horizontally, which means you still have some kinetic energy. So this gravitational potential energy has to be distributed between gravitational potential energy and kinetic. And some of that kinetic energy here steals away from the gravitational potential energy, and it doesn't allow the car to go as high as point A. So I think the answer should be less. Yeah. Okay. Now RT25. Starting from rest, Angel and Brittany skateboard down a hill as shown. Angel rides down the steep side while Brittany rides down the shallow side. Angel has more mass, so she has more mass. So I'm just going to write that as an uppercase M, here a lowercase m to remind myself. Assume friction and air resistance are negligible. Is the speed at the bottom of the hill greater for Angel, greater for Brittany, or the same? Well, since they have the same gravitational potential energy, so their MGH, okay, well, they don't have the same gravitational potential energy, I'm sorry, because Angel is heavier. But I can write the conservation of energy and say, well, gravitational potential energy is MGH, that has to equal 1/2 mv squared, right? So the mass is irrelevant. So at the bottom, they should have the same speed, okay? Is the time it takes to get to the bottom of the hill greater for Angel, greater for Brittany, or the same for both? The time, it's greater for Brittany, okay? Well, it's shorter for Angel because she has a shorter distance, kind of, and a bigger acceleration. So the time to get to the bottom is greater for Angel, okay? So that's I. Okay, so I can't see that. So is the work done by the normal, I'm sorry, I missed something. I'm sorry, I was reading the wrong thing. Is the time to take to get to the bottom of the hill, it's greater for Brittany. Yeah, Brittany. Because she has a longer distance, right, and a smaller acceleration. So it's going to take longer for her to get to the bottom. I'm at C. Is the work done by the gravitational force on the skateboarder greater for Angel, greater for Brittany, or the same for both skateboarders? Well, I think it's greater for Angel, and the reason for that is the work done by gravity depends on the mass and the height, is that MGH. And the height is the same, but Angel is heavier. So more work is done on Angel than is done on Brittany. So the answer for that is I. Okay. Is the work done by the normal force, blah, 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 blah? Well, the normal force is always going to be perpendicular to the ramp, right? So it's never going to do any work because it's always going to be perpendicular to the direction of travel. There's always that 90-degree angle between the direction of travel and the normal force. Is the kinetic energy at the bottom of the hill greater for Angel, greater for Brittany, or the same? Well, I think earlier we said they have the same speed, right? If they have the same speed, kinetic energy is 1/2 mv squared. If the v is the same, the one with the heavier mass will have to have more kinetic energy. I mean, just think about it logically. If she's sliding down the ramp, all right, if something is in the way, if there is a person here, if she hits that person, she's going to really hurt that person. She's not going to hurt them as much because she has a smaller mass, which means a smaller kinetic energy. So the speed is the same at the bottom, but not the kinetic energy. Okay. A roller coaster starting from rest descends 35 meters in its initial drop and rises 23 meters. In other words, the height is 35 meters, so it does this. Okay, so I'm going to pick this point here as 0 for gravitational potential energy. This is 35 meters. That's the initial height. And it rises 23 meters here. First hill, okay. Which has a circular shape over the top. So this is kind of like part of a circle. Okay, there's no circle there, but it has the shape of a circle. If the passenger at the top of the hill feels an apparent weight, well, the apparent weight is basically the same thing as talking about the normal force, okay? Equal to half the normal weight. So this Fn up here I think I should label this. I'm going to label this A, B, and C. The Fn is basically half of mg up there. What is the radius of curvature of the first hill? Okay. So I think I have to do some circular motion stuff here. Okay, so let's look at the forces acting on this person when they are up here. Okay. So you have your normal force, okay, and you have your mg, bigger. So let's write the net centripetal force equals mv squared over r. This is circular motion stuff, right? So towards the center is positive, so it should look like mg minus the normal force is mv squared over r. Well, Fn is half of mg, okay? So mg minus half of mg, it just leaves us with half of mg, right? So the masses will go away. So now if I want to find the radius, I'm stuck. I need to figure out the v first before I can find the radius. So to figure out the v, right, or maybe the v squared, I would do conservation of energy. So I would say the gravitational potential energy at point A plus, there's no kinetic energy at point A, it's starting from rest, okay, equals the gravitational potential energy at point C plus the kinetic energy at point C. Now this is mgh equals mgh, right, plus 1/2 mv squared. So I'm not going to solve for v. I'm actually going to solve for v squared because I really need v squared here. I don't need v. Right? So the mass is gone, right? So and I think I can multiply everything by 2 here. So v squared is going to be equal to this quantity here, which is 20 times, I'm factoring out, doing some mental math, 35 minus 23, so that's 12, so that should be 240. So this v squared is 240. So now we're looking at 1/2 of g, so I'm taking this down here. So that's 5 equals 240 over r, right? So r is 240 over 5. So 240 over 5. But 240, I don't need to put in the calculator actually. 240 over 5 is 48. Okay. We're looking at 42. A stone is released from rest at a height h at the left side of a loop-the-loop as shown in the figure. There is no friction but no air resistance. If the radius is r, what is the minimum height h for which the stone will not fall? If you remember, we did these problems like this in the past, and the way we did this, we say, well, let it fall, right? Let's treat the problem as if it's going to fall, and then we'll make a decision whether the radius should be bigger or smaller. Right? I mean, the height should be bigger or smaller than when we find. All right, so let's try this. Okay, so this is on the inside, so the forces are Fn and mg, right? Now, in order for it to fall, right, Fn has to be 0, right? So now let's write the circular motion, Newton's second law for circular motion. So mg plus Fn is mv squared over r. Okay, so we're going to say, well, you know what? Let's make Fn 0. And then the height just has to be higher or greater than whatever we find. Okay, so this is 0. The mass is gone. So now we're looking at V square equals G times R. So we'll leave that, and then we'll do conservation of energy. I'll call this A and B. At point A, I have mgh basically. That's all I have. I have gravitational potential energy. If I consider this point here as 0 gravitational potential energy, that's my reference point for gravitational potential energy. Equals, when I'm up here, I have to deal with kinetic energy and gravitational potential energy. Now, gravitational potential energy here is mg times the new height, which is, if you see, look at it, it's 2 times the radius, the diameter, plus 1/2 mv squared. Okay, so I can divide everything by the mass, right? I'm not going to solve for v. I want to solve for v squared and maybe do a little substitution here, right? So if I multiply everything by 2, this is what I'm looking at. So I'm going to manipulate this a little bit. This is uppercase R. Okay. Okay. So let's see. So v squared here is equal to 2gh minus 4gr. I think it's right. Yeah, 2gh minus 4gr. Yeah. So I'm going to come here and say 2gh minus 4gr equals gr. Now, if I think I can just divide everything by g, maybe move this 4r to the other side. So I'm looking at 5r divided by 2. So at 5/2 r, right, they will fall off. If you think about it conceptually, okay, your height has to be more because you want to come in with more more gravitational energy to stay on that track. So the answer is it has to be greater than 5/2 of r. Okay, number 43. As shown in the figure, a 4-kilogram block is moving at 5 meters per second along a horizontal frictionless surface towards an ideal spring. An ideal spring means like it obeys Hooke's law, there is no friction. That is attached to a wall. After the block collides with the spring is compressed a maximum distance of 0.68. What's the speed of the block when the spring is compressed to only half the maximum distance? All right, so let's start with the half maximum distance, and if we need full compression, we'll worry about it later. So when it's halfway compressed, so we come in with kinetic energy, okay, initial. There is no work in between, okay, and that's all there is, and that should equal to the energy after the spring is compressed. Now, when it's halfway compressed, okay, there is still some kinetic energy left, plus energy stored in the spring at the end. Okay, so we're looking for the speed for this kinetic energy. So now this is just going to be 1/2 mv squared, okay, equals kinetic energy final. We don't know, so that's 1/2 mv squared, or 4 v squared, plus when it's halfway compressed, I think we can write 1/2 k, that's the constant of the spring, and it's 0.34 squared. See, the problem is that we have 2 unknowns. We have the v and the k, right? So that's when we go and use the full compression to maybe find the k. So when it's fully compressed, you have this much kinetic energy coming in, okay? When it's fully compressed, the only energy that you're dealing with is energy stored in the spring, 1/2 k x squared, which is 0.68 squared. Yeah. And So I can get rid of these guys here. So K is going to be equal to 216.26 newtons per meters. You can take that, put it here, and you're pretty much done. Okay? So now the V will be equal to 4.33 meters per. All right, I'm going to look at 43, but just try to do it with, I'm going to try to do it with proportions instead of like doing it in 2 steps. So let's see if we can handle this. This might be a little tricky. Okay. So initially we come in with 1/2 mv square energy. Now when the spring is compressed halfway, now let's just think about this. If it's compressed halfway, only a quarter, and the reason for the quarter, because of that x squared, only a quarter of this energy is elastic potential energy. I hope you can see that. Okay? Now, if a quarter is in the form of elastic potential energy, 3/4 of this, right, is in the form of kinetic. So basically, I can say that my kinetic energy, when it's compressed halfway, is my kinetic energy, which is 1/2 mv squared, is 3/4 of the energy that I was coming with. Okay, and this is 5 squared. So I hope we can see that. And this is much quicker than the way I did it earlier. And you don't even need to know the value for the mass. So I can get rid of these halves. Okay, so the V is just going to be, I guess, radical of that number, whatever, 75/4 it looks like. And that should give you whatever answer I gave you earlier. Right? Okay. So let me just try that. Yep, should give you the same exact answer, but in a much, much quicker way. So if you just know the relationship between energy and the amount of stretch and speed, just keep in mind that there is a square on top of the x and there is a square on top of the v when you're dealing with either kinetic energy or elastic potential energy. All right, that's done. All right, so let's look at number 44. Okay. Now, in a previous video, I defined the G force as the ratio of the normal force to the Fg. Okay? So basically, that's how much more heavier or lighter you're going to feel compared to your own weight. So this is 55 meters. We're starting from rest. If we're not starting from rest, we have to take that kinetic energy into account. So now to find the potential energy here, the mass of this object is 50 kilograms. It's basically just mgh, and we should get 27500 joules. Okay. Now, my total energy anywhere on this roller coaster has to be 27,500. Kinetic energy up there is 0. This is 0 meters per second. Okay, because they are not moving. The centripetal force is 0 because there is no, this is a flat surface, it's not even a circle. Okay, and centripetal force is basically mv squared over r, right? Now, the r is infinite. In other words, it's a flat surface, so that's going to end up being a 0. Okay, so this is 0, right? No, the F1, the centripetal force is 0. The F1 track, which means the normal force, basically that's just going to be equal to mg. So that's 500. Okay? And the g force is just 1. Because you're on a flat surface, you're going to feel that 50 kilograms is going to have a weight of 500 newtons and a normal force of 500 newtons. So the G force here is 1. Okay. Now let's go to this point here. I guess I'll label it B. I'll label this as C. The height here is 40 meters. Okay. Okay. So the potential energy is just going to be 50 times 10 times 40, which is 20,000 joules. Okay. The kinetic energy will be the difference between these two energies here, between these two values for potential energy. So it's going to be 7,500 joules. Okay. The velocity, you would just do kinetic energy is 1/2 mv squared, and you pretty much have everything you need. You have your k, you have your mass, you can find the speed, and it's 17.32 meters per second. To find the centripetal force, it's mv squared over r. So basically that's the net force in circular motion. You have the mass, you just found the v, you can do and divide by r. Here, if you want to do it quickly, and I'll leave that up to you, mv squared is basically just 2 times k. So it's really up to you how you do it. So it's 2 times 7,500 is 1,500 divided by 20. Okay, so that should give you 750. Just if you want to do the math quicker. The F on track, which means the normal force, now we have to go back to the centripetal force stuff. So when you're up here, okay, you're on the outside. So you have your normal force and you have your weight. Now your weight is got to be greater because the acceleration is to the net centripetal force is towards the center, which is here. So I think we can write mg minus Fn equals mv squared over r, and oh no, they're on the outside here. This loop is on the outside. Sorry, yeah, this is on the outside. I mean on the inside. Fn plus mg, yeah. So Fn is just going to be mv squared over r, which is basically the centripetal force minus the mg, which is 500. So this should be 250. And the g force is just going to be half. No units, because it's the ratio of two forces. Okay. When you are down here, you're on the inside. So you have your normal force, which is greater than your mg. So down there, we need to write Fn minus mg equals mv squared over r. Okay, so Fn will be equal to mg plus mv squared over r. Now it's a different v. It's the v down here. So let's figure that out. So the potential energy at the bottom is 0 joules. Now all this potential energy, this gravitational potential energy you had at the top here, gets converted into kinetic energy. So law of conservation of energy, and here we're assuming that there is no friction on the tracks. The V is going to be kinetic energy is equal to 1/2 mv squared. So we should have a V equal to 33.17 meters per second. Okay. Now the centripetal force is basically mv squared over r. So m times that 33.17 squared over 20, and that should give us 2750 newtons, right? Now to find the Fn, what I'm circling here is 2750. That's your centripetal force. The mg is 500, so this should become 3250 newtons, right? That's 2750 and plus 500. The g force is the 3250 divided by 500. So that looks like it's 6.5. And in a previous video, I said that if the loop is a circle, okay, the difference between the g-forces between the top and the bottom will always be 6, right? So I'm not going to prove that. Maybe we can prove it in class. All right. Now you see that at the bottom, the g-force is 6.5. That's not comfortable, right? So to avoid that problem, what the engineers do is that they make, and the reason for that is when I had the equation written, I had Fn minus mg equals mv squared over r, right? So which means Fn equals mg plus. Okay. Now we have no control. If I want to reduce the Fn, because by reducing the Fn, I'm going to reduce the g-force. If I want to reduce the Fn, let's see what variables I can change. I cannot change the mass. I cannot change the g. I cannot change this mass. I cannot change this velocity. That's dictated by the law of conservation of energy, right? So, but I can play with the r. So I think if I make r large, if I give it a bigger curvature, this whole expression will be less, okay? So if I lower this expression, I'm lowering this whole addition, I'm lowering the Fn, which means I'm lowering the numerator in the g-force formula, which means I'm going to end up with less of a g-force. So what the engineers do is they make the bottom loop wide, having a big angle, a big radius. Now let's see what they do at the top. At the top, you're going to have Fn plus mg, so I'm going to move the mg on the other side, plus mv squared over r. So let's see what we can control. I cannot control, the only thing I can control really is the r. So if I make r, so at the top, you want to increase the Fn for safety reasons, right? You want to make sure that those people stay on the track, right? So if I want to increase Fn, I think I have to increase this quantity here, right? Because I have to subtract, so I have to increase this somehow. In order to increase this expression here, I have to make the radius smaller. So what the engineers do is what's on the next page, and you can read about it. I have a little information about how they designed the loops. So basically, we're going to make we're going to make the bottom of the loop wide but narrow at the end, and this is not drawn to scale. You can probably see that. Okay. All right. So this is 55 meters. It's the same problem as before. I think this was 50 kilograms. Okay. Now the potential, a lot of the numbers are the same. Let me just cheat here. So 27,500 joules, 0 was 0 newtons. This is 500 newtons, and this is 1. This was 0, 27,500 joules. All the energy, the values for energy will be the same. Okay, but what changes is the centripetal force and the g-force and all that stuff. So the same rules apply. When you are here, you get your Fn, you get your mg. So Fn minus mg is your mv squared over r. You can find the mv squared over r here, which is the centripetal force, by doing m times that number, right? Mv squared divided by, it's a new radius now. The radius is 45. It's the radius of this curvature, in other words. So this is going to curve out more. So maybe it extends. Yeah, the 40 is way out of place here. So it's not drawn to scale. You want to find the normal force. You can just use the centripetal force business, right? Okay. So think you should be able to do this one with no problems. So it's a combination of a circular motion and conservation of energy. All right, let's look at 46. The drawing shown a version of the loop-the-loop trick for a car. If the car is given an initial velocity or speed of 4 meters per second, what is the largest value that the radius can have if the car is to remain in contact with the track? Okay. Now, the way we treat this is that we're going to say, okay, you know what? Let's try it and allow the car to fall. And then we'll make a decision about whether the radius should be bigger or smaller than that value. So when I'm up here, when the car is here, we have the Fn and the mg acting on it. Okay, so I'm going to do a combination of conservation of energy and circular motion, right? So I'm going to start with the circular motion business, right? The centripetal force, which is mg plus Fn, is mv squared over r. Right, so I'm going to make this Fn 0. So I'm going to find the speed or an expression for the speed for which the car will no longer make contact with the tracks or the road. So v is basically going to be equal to square root of g times r. So technically it should be greater, right? Because at that speed they're going to fall. So you want to be coming with a higher speed. All right, so yeah, the mass crosses out here. You can manipulate this equation. Now let's do the conservation of energy. The energy down here is 1/2 m v squared. Okay. This velocity here is the velocity at the top. Okay, equals mgh. Mg, the h is 2 times the radius plus 1/2 m v squared. Well, that's the v at the top, so v squared is just going to be gr. Okay, so we can divide by the mass. So this should give us, what is that? 8 equals, now I have 2 grs and I have half a gr, so that's 5/2 gr, right? So I think I can put in a 10 here. All right. So that looks like it's 16 over 50, right? Here's r. So 16 over 50. Okay, so that's 0.32. Okay, so the radius has to be less than 0.32. I mean, think about it logically. If it's more, right? If it's higher up, you should be coming with the greater kinetic energy to make it up to the top. So you have to be less than 0.32 meters. All right, RT26. Okay, Abby and Bonita decide to race up a hill that is 30 meters high. Abby takes a pad that is, okay. So this is 60 meters. Okay, this pad here. Okay, this path here is 100 meters. Abby takes 40 seconds to accomplish this. Bonita takes 30 seconds. They both start from rest at the same height and stop at the top. Abby has, so she has 70 kilogram mass. She has 50 kilogram mass. Okay, so that's their weight. Okay, so the weight is 700 and 500. Is the work that Abby does in going up the hill greater, less than, or the same as the work Bonita does? Well, the work done is basically mgh. You have to work against gravity, right? Both of them have to work against their own weight. Okay. Now, the height is the same for both. The g is the same, and the one that's going to do more work is the one that's heavier, which actually makes sense, right? This is similar to the lab we did in going up the stairs, Okay. So Abby will do more work. So is the work that Abby does greater? Yeah, it's greater. Okay. Okay. The next question is the power generated by Abby in going up the hill greater than, less than, or the same? Well, let's look at the power. The power is equal to work divided by time, right? Now, the work done by Abby, so it's going to be 700 H, yeah, divided by her time. So this is Abby. The power for Bonita is going to be the work done by Bonita divided by the time it takes her. Well, her work is 500 times H, it's mgh in other words, divided by 30. And if you compare these two, you're going to find that the left expression is bigger. So the answer is greater than. All right, RT27. Which is the last thing in this packet. Work and power. Amanda and Bertha are in a car race. Their car have the same mass. At one point in the race, they both change their speed by 10 meters per second. So this one is going from 10 to 20 and the other one is going from 20 to 30. Is the work that Amanda's car does while speeding up greater than, less than, or the same? Now, conceptually thinking of it, logically, without physics, I hope you can see that it's going to take a lot more effort to go from 20 to 30 than to go from 10 to 20, right? Because you're already at a higher speeds and you want to go even higher. Now, let's see if the physics confirms that. Let's see if the, okay. Energy initial plus work equals energy final. All right. Here we're only dealing with kinetic energy. We're on a flat surface. Okay. So I can say that the work is basically equal to the change in kinetic energy, which is 1/2 m the final velocity square minus the initial velocity square. Now, the difference here, the difference of squares is definitely less than the difference of squares over there. Here, I think we got a difference of 300. Over there, I think we get 500. So it's definitely, there is more work being done on the other side. The next question is the power generated by Amanda's car greater than, less than, or the same? Okay, it's got to be less than, because the amount of time is the same, but Amanda's car does less work. So power is your work divided by time, is how fast you do the work. So the time is the same. So comparing the powers is basically just comparing the work done. Okay. All right, so we're done with the packet basically. Now I'm going to try, I'm going to try to show you why the difference in the g-force in a circular loop is 6 g's. All right, so let's try that. When you're up here, you have your mg and you have your fn. When you're down here, you have fn and you have mg going the other way. Now, fn has to be bigger here. So let's do the centripetal force business. So mg plus this fn, or I can call it just, instead of fn, I'm just going to call it n. So this is n at the top, okay, equals mv square at the top over the radius. Now the radius is the same, okay. At the bottom, it should be n at the bottom, okay, minus mg equals mv at the bottom square over r. So I'm going to try to isolate the ends, right? Okay, because what I'm trying to, okay, actually I can do the difference because we're saying that, okay, so let's try, maybe we can find an expression for n, then do the division. Yeah, let's try that. So minus mg, okay, this is going to be plus mg. So to find the g force here, you can just divide by mg, divide by mg. So this is going to be mgr. The other side is going to become a 1. Okay. And if I divide by mg, I get a 1 here. Yeah. Okay. So I'm going to subtract. Yeah. So actually, I'm going to get rid of this m's. Okay. All right, and I'm going to subtract. So because this is the g force basically at the top, and this is the g force at the bottom. And I know at the bottom is greater, so I'm going to subtract in this direction to see if that difference is really a 6. Okay. So n, actually I'm going to call this g force bottom, g force top. Okay, so g force bottom minus g force top, okay, equals, so let's do the math here, let's see what we get. So it's v, the bottom square over rg, yeah, minus v top square. I can put them together since there's already a common denominator, which is a good thing. Plus 2, it looks like, right? Yeah, because it's 1 minus negative 1. All right. So now we just have to worry about this difference here. Okay. Okay. Now this is r. This is also r. Okay. So let's just say my kinetic energy down here, right? So I'm going to do conservation of energy. It's 1/2 m v at the bottom square. That should equal to the total energy at the top is equal to 1/2 m v at the top square plus, now there is what do you call it? There's gravitational potential energy. So that should be mg times 2r. All right, so let's see what we can do here. So I think I can get rid of this mass. Okay, maybe if I get rid of this half, basically I multiply everything by 2. Oh, I see a 4 and I see a 2 in there. Something's going to happen. Maybe I can subtract. I'm looking to get that top expression with the difference of the velocities. If I subtract here, this is equal, right? I need to divide it by gr or rg. Okay, here it is. Okay, so basically this whole thing is just 4. So you come in here, you put in a 4 plus 2, 6. And this is only true for a circle because remember, we had to take into account this 2 times r, which is that distance here, which is basically only true for a circle. And that's the proof because some of you asked me to show you why. All right, and I'm done.